Hi everyone, welcome to the lecture series on sliding mode control. In this lecture series, we will be discussing the basic concepts of sliding mode control or SMC and also discuss its numerical implementation using various examples. In this first lecture, we give a brief introduction to first order SMC, which is also called as classical SMC. We start by discussing the basic idea of sliding mode control using an example of an integrator system. Then we briefly discuss about the key features of first order SMC. Sliding mode control or SMC is a modern control approach which is based on a nonlinear discontinuous control law. The discontinuous control law can be implemented using relays or switches, and SMC uses relays as the basic control element. In control theory courses, we might have seen various control elements such as proportional element, saturation, relay, etc. A proportional element can be graphically represented as in figure 1, which gives the control input u as equal to k times e, where e is the error variable, which can be either the output error or the state error. The small letter k is the linear gain, which is also equal to the slope of this line. Here we can see that we have a linear relationship between the control input u and the error e. And as the error e increases, the control input u is also increases proportionally. So the value of the control input can be arbitrarily large and it can take any value in the interval from minus infinity to plus infinity. However, in practice, we have to limit the control values by some upper bound and lower bound due to physical limitations, energy constraints, safety reasons, etc. This leads to the saturation element in which we limit the control input by an upper bound plus k and a lower bound minus k. Note that here this capital K is the bound and small letter k is the linear gain. For small error values, or in particular, the error values in this interval highlighted in green color, the control input u is decided by a linear relationship where u is equal to small letter k times e. And for higher error values or values that are not in this region, we limit the input by either plus capital K or minus k. Note that here this upper bound and lower bounds can be unsymmetrical as well, which means we have an upper bound as plus k1 and a lower bound as minus k2, where k1 and k2 are different finite constants. Here we can see that the saturation function is defined by a nonlinear relation, which we can also call as a piecewise linear relation. We can also see that as the value of the bound capital K increases, this will goes up and this interval in green color for this linear region increases. Then as the bound K tends to infinity, the saturation will become a proportional element, which we denoted here by this arrow. Another observation is that if we increase the linear gain or the small letter k, keeping the bound or this capital K fixed, then the slope of this linear portion increases and the width of this green interval decreases. Now, as the gain k becomes infinity, this line becomes vertical as shown here, and the width of this green region becomes 0, and it results in a relay element. Now, in the relay element, the control input u is defined using a signum function as u is equal to k signum of e, where signum of e takes a value of plus 1 if e is positive and minus 1 if e is negative. Then k times signum of e takes a value of plus k if error is positive and a value of minus k if error is negative. At e equal to 0, the control input u can take any value between plus k and minus k as shown here. However, in practice, we can fix the input to either minus k or plus k for e equal to 0. In short, we can say that the proportional element and relay are limiting cases of saturation element. Also, relay and saturation are nonlinear control elements, whereas proportional element is linear. In SMC, we use a relay as the basic control element, and since relay is a nonlinear control element, SMC is a nonlinear control approach. Figure 2 shows the block diagram of SMC in a closed loop control configuration, which consists of a dynamical system and an SMC controller. The dynamical system consists of an actuator, plant, and sensor or estimator, which we combine together and call as the system. The physical variables in the system that we measure using some sensors are called as output variables. And the minimal set of variables in the system that can capture the entire dynamical behavior of the system are called as state variables. And in SMC, we compare the output or state with its reference value to generate an error signal. And the SMC controller computes the control input, which is computed as a function of the error variable. Now, in order to design the SMC control law, we need a mathematical model of the system, which are usually in the form of differential equations that describes the dynamics of the physical variables in the system. Therefore, in this lecture series, we assume that the mathematical model of the system are available and which are in the form of differential equations or state equations. To illustrate SMC, we consider an example of an integrator system, which is a first order system and is defined by the differential equation x dot equal to u plus d, where x is the state variable, u is the control input, and d is the disturbance input. Here, the variables x, u, and d are continuous functions of time. So we have x equal to x of t, u equal to u of t, and d is equal to d of t. And we denote x of t0 as x0, which is the initial state. Here in the block diagram, we have x dot equal to u plus d, and by integrating x dot, we get x. Now we denote the output y as equal to x, and the output reference yr is equal to 0, and the disturbance d equal to 0. And the proportional control law is defined as u is equal to ke, which is equal to k into yr minus y, which is equal to minus kx, since yr equal to 0 and y is equal to x. And by substituting for u and d in this differential equation, we obtain x dot equal to minus kx, which is a first order linear homogeneous differential equation, for which the solution is x of t equal to x0 into e raised to minus kt, where small letter e is the natural exponent, and here this is an exponentially decaying function. And as t tends to infinity, this term will become 0. Now in the case of SMC, the control law is defined as u equal to k signum of e, which is equal to k signum of yr minus y. Since yr equal to 0 and y equal to x, this will become k signum of minus x, which we can rewrite as minus k signum of x. Here, for x greater than 0, we have signum of x equal to plus 1, which gives u is equal to minus k and results in the dynamics x dot equal to minus k. And for x less than 0, we have u is equal to plus k, which gives x dot equal to plus k. This implies that the magnitude of x will decrease at a rate of capital K, and x will become 0 in a finite time Ts, where Ts equal to modulus of x0 by k. Next, we discuss the simulation of this example for an initial state x0 equal to 2. The simulation step size or sampling period t is equal to 0.001. The proportional gain or small letter k is equal to 1, and the SMC switching gain or capital letter K is equal to 1. Figure 4a shows the response with the proportional control law, which shows the state in black color and the control u in red color. Here the state x starts from the initial value x0, which is equal to 2, and converges to 0 exponentially. We had the control input u is equal to minus kx, and we had k equal to 1. So therefore u will be equal to minus x, which results in the plot of u as shown here. Now for the integrator with SMC, the response will be as shown in figure 4b, in which the state starts from an initial value of 2 and converges to 0 in the ideal case. However, in practice, the state oscillates around the reference value, which can be observed from this zoomed plot. This is due to the discrete time implementation of the control law, in which we update the control law only in every t instance, and we have t is equal to 0.001. Here, the SMC control law gives u equal to minus k signum of x, and the switching in capital K is chosen as plus 1, which results in u equal to minus signum of x. Therefore, if x is greater than 0, then u will be equal to minus 1, and if x is less than 0, then u will be equal to plus 1. Here, during this initial period, we have x is greater than 0, so u will be equal to minus 1, and once x is decreases and crosses 0, the u will switch to plus 1, and after that it will start to switch between plus 1 and minus 1, and the state will start oscillate around 0. Here, this high frequency oscillation of the output variable around the desired value is called chattering, which is in fact a shortcoming of SMC. and we will discuss chattering in detail in the upcoming lectures. Next, we introduce some disturbance into the system and look at the response. For a sinusoidal disturbance of the form d of t equal to a sin omega t, the dynamics with the proportional control law gives x dot equal to minus kx plus a sin omega t, where this is the u and this is d. Note that in the case of no disturbance, we had x dot equal to minus kx, which is a homogeneous differential equation, and here we have a non-homogeneous differential equation due to this disturbance term. Now, from the basic differential calculus, the solution of this first order non-homogeneous differential equation will be the sum of homogeneous solution and particular solution as in equation number 9. Here, the homogeneous solution will be an exponential function as before, and the particular solution will be in the same form of the disturbance function and can be represented as a sin omega t plus phi, where this capital A is the amplitude and is equal to this value, and phi is the phase. In this response, this exponential term will be converging to 0 as t tends to infinity. However, the sinusoidal term will remain there and results in steady state oscillation. Here the magnitude of this oscillation depends on the capital letter A, which depends on the disturbance amplitude small letter a and the linear gain small letter k. Here we can observe that as k increases, the amplitude of oscillation or capital letter A decreases. And as the linear gain k tends to infinity, the oscillation amplitude capital A tends to 0. Similarly, for the disturbance d is equal to a sin omega t, the SMC controller results in x dot equal to minus k signum of x plus a sin omega t. Now here, if we choose the switching gain k is equal to small letter a plus neta, where neta is some positive constant, we can ensure that x dot is less than or equal to minus neta signum of x. This is because of the reason that sin omega t is a bounded function which is bounded by plus 1 and minus 1. So the magnitude of this term will be bounded by a. Now if we select k is equal to a plus neta, then this term will become dominant and x dot will be always less than or equal to minus neta signum of x. Therefore, the magnitude of x will decrease at a rate bounded by neta, and x will become 0 in a finite time ts, where ts is less than or equal to x0 by neta. Next, we consider the simulation of the integrator system with a sinusoidal disturbance as given here. The initial state is chosen as 2, and the proportional gain and switching gain are chosen as 1. Figure 5a shows the response with the proportional controller, and here we can see that the state x starts from the initial value 2 and converges. However, due to the disturbance, it does not converge exactly to 0. We are seeing that in the case of proportional controller with disturbance, the overall response will be a sum of an exponentially decaying term and a sinusoidal term. Here this exponential term will converge to 0 as t tends to infinity. However, the sinusoidal term will remain in the response and results in steady state oscillation. So this oscillation in steady state is basically due to the disturbance term. Now for SMC, we can see that the state starting from the initial value which is 2 and converging to 0. Here the control input starts from minus 1, and as the state crosses 0, the control input starts between minus 1 and plus 1 at a high frequency, which maintains the state approximately at 0. Theoretically, we can have infinite switching frequency in continuous time implementation. Therefore, we can maintain the state exactly at 0. However, in practice, the states will oscillate around the reference value with a small amplitude and high frequency, and this leads to chattering. Next, we briefly discuss the case with the non-zero reference, where yr is equal to xr, which is a non-zero constant. In that case, the system dynamics with SMC becomes as in equation number 12, where xr also appears here. Here also, if we select the switching gain k as a plus neta, we can ensure that the magnitude of x will decrease at a rate of at least neta, which results in x of t equal to xr in a finite time ts, where ts is bounded as in equation number 13. And this implies that after a finite time, the system state reaches xr and stays there, which gives x of t equal to xr for t greater than or equal to ts. This means that after a finite time, this first order system will become a zeroth order system or a static system. Next, we briefly discuss some of the features of first order SMC. In SMC, we use a switching function for computing the control input, and the switching function is a mapping from the state or output space to the input space. In the case of single input system, the switching function will be a scalar valued function, and we usually call it as the sliding variable. Now in the case of first order SMC, the relative degree between the sliding variable and the control input u will be equal to 1. This means that the control input appears in the first derivative of the sliding variable. For example, if the relative degree between s and u is equal to 2, it means that the control input appears in the second derivative of s. In that case, the first derivative of s does not contain any terms with the u, and the terms with the u starts appear only in the second derivative onwards. In general, if the relative degree between s and u is equal to r, then the control input appears in the rth derivative of the sliding variable for the first time. Now, if r equal to 1, we call it as the first order SMC, and if r is greater than 1, we call as the higher order SMC. Now, in the initial few lectures, we will be focusing on the first order SMC, which is also known by the name of classical SMC. And the key features of classical SMC are reduced order dynamics, discontinuous control input, non-uniqueness of solutions, chattering, etc. Note that most of these features applies to higher order SMC as well, and we will discuss these features in detail in the upcoming lectures. Now, in the integrator example, we can define the switching function or the sliding variable as in equation number 14, which is chosen as the output error, and it is same as the state error in this example. And we define the sliding surface as the region in the state space for which the switching function or the sliding variable equal to 0. So the sliding surface is defined by s of x equal to 0, and this gives xr minus x equal to 0, which gives x equal to xr. Therefore, in this example, the sliding surface is a point. In general, based on the dimension of the state and input space and selection of the switching function, the sliding surface can be a point, a line, a plane, hyperplane, or it can be some nonlinear surfaces. Now, if we take the derivative of the sliding variable, we get s dot equal to xr dot minus x dot. And for a constant reference, we have xr dot equal to 0, and we have x dot equal to u plus d. So this will give s dot as minus u minus d. Here we can observe that the control input appears in the first derivative of the sliding variable. Therefore, the relative degree between s and u is equal to 1. Next, we discuss about the control input in the case of first order SMC. And we have already seen that in first order SMC, the control input appears in the first derivative of the sliding variable. Therefore, in general, the derivative of the sliding variable can be represented as in equation number 17, where a of tx and b of tx are some function of states. Normally, b will be a constant term, and we assume that b is known and a is bounded. Then we can select the control input u as minus 1 by b times k signum of s. And if we substitute this here, we obtain s dot equal to a minus k signum of s. And if we assume a is bounded by c and select k equal to c plus neta, and then we can ensure that s dot is less than or equal to minus neta signum of s. And by multiplying both sides of this inequality by s, we can rewrite this as s into s dot less than or equal to minus neta mod s, where we use the relation s into signum of s equal to mod s. This ensures that the magnitude of the sliding variable is decreased at a rate of at least neta, and sliding variable converges to 0 in a finite time ts upper bounded by mod s of 0 by neta, where s of 0 is the initial value of the sliding variable. And we call this criteria as the neta reachability condition, which is normally used for designing first order SMC control law. In general, we can rewrite the uncertain term a as a sum of nominal term and unknown terms, such as a equal to a0 plus a bar, where a0 is the known terms in a and a bar is the unknown terms. And we can assume that a bar is bounded by c bar. In that case, we can modify the control input as u equal to minus 1 by b a0 plus k signum of s. So here basically we added the known terms in this control law. And for this control law, we can obtain s dot as a bar minus k signum of s. And we can select the switching gain k as c bar plus neta. And this control law is a sum of a continuous term and a discontinuous term. And therefore, we can represent the general control law for first order SMC as in equation number 21, where UC is the continuous part of the control signal, which cancels the nominal or non terms in S dot, and UD is the discontinuous part of the control signal, which deals with the uncertain terms in S dot. Next, we briefly discuss about the non-uniqueness of solution in the case of first order SMC, and we can recall the integrator system example that is discussed earlier. For YR is equal to XR and the disturbance D of t equals A sin omega t, we have the dynamics of the integrator system with SMC will be as in equation number 22. Here this term is the control input U and this is the disturbance term. Here we can represent this overall term as f of x, which is a nonlinear function of x. And we can plot this function f versus x, which is given in figure 6. Here we can see that this function f is discontinuous at x equal to xr, or it has an infinite slope at this point. Now from nonlinear system theory, in order to have a unique solution to the differential equation x dot equal to f of x, the function f should be Lipschitz. Here by Lipschitz, we mean that the function should have a finite slope across all its domain. However, in this case, we can see that at x equal to xr, the slope of the function is infinite. Therefore, the function f of x is non-Lipschitz in the case of SMC, and this results in non-uniqueness of solution in the case of SMC. And we have observed that in the case of integrator system example, for all initial condition, the solution becomes x of t equal to xr after a finite time period. Here by non-uniqueness, we means all the initial condition will result in a same solution after a finite time period. In short, we can say that SMC is a nonlinear discontinuous control approach which uses a signum function in the control law. And in the upcoming lectures, we will discuss SMC in detail with more examples. That completes this lecture. Thanks for listening.